Okay, this second example is fairly similar to the first example. The differences here are that we have an externally applied bending moment of 15 kilonewton meters, and we have a uniformly distributed load, or a UDL. So all that is a load that has a constant intensity over a particular length. So again, we want to work out what are the three unknown reactions. And again, noting that there are three, we know that we can use the equations of equilibrium to solve for them. So now the way I handle a uniformly distributed load is I replace it straight away. As soon as I see that, I go in and I replace that straight away with an equivalent point load, okay, or an equivalent concentrated load. So that's simply going to be the magnitude of the load, or rather the intensity of the load, multiplied by the length over which it acts, and that will give me the total amount of load, if you like. So if we have 2 kilonewtons per meter, and it's acting over a length of 5 meters, well then in total I have 10 kilonewtons. And I know that the resultant of that load will be right in the center of the UDL itself. So instead of having this UDL, it'll be like getting rid of that, okay, and having a resultant, and I'm going to indicate the fact that it's a resultant by that squiggle there, a resultant point load of 10 kilonewtons per meter. Or rather, no, that's a UDL. It's going to be 10 kilonewtons full stop. All right, so we have 2 kilonewtons per meter acting over 5 meters gives me 10 kilonewtons. Now I can go ahead and process this structure exactly the same way as I did with the previous structure. So the first thing I'm going to do is evaluate the sum of the horizontal forces. So I know, as usual, the sum of the forces in the x direction must equal 0. I'm going to assume to the right is positive, so I will have HA. Now let's look, we literally only have HA. There are no externally applied horizontal forces. So that simply means that HA equals 0. So it's an important little point to note here. A pin support, okay, has the potential to generate a reaction. So if an externally applied horizontal load comes onto our structure, well then we can generate a horizontal reaction to that load at a pin support. But if there are no externally applied horizontal loads, well then there'll be no reaction. And that's what we see happening in this case. So HA equals 0. Now we can look at the forces in the vertical direction. So the sum of the forces in the y direction must equal 0. I'm going to assume upwards is positive. And what do we have? We have VA plus VB, my two reactions, minus the 10 kilonewtons, which is the resultant of the UDL, minus 7 equals 0. Let's just tidy that up a little bit. VA plus VB equals 17. Okay, and similarly to the last case, we now have a second equation with two unknowns. So we're going to use our third equation to get us across the line. So what I'm going to do, exactly as I did before, I'm going to take the sum of the moments. Now I could take the sum of the moments about any point. And if I say, for example, I took the sum of the moments about a point in the middle of the beam, I would end up with another equation, a moment equation that has two unknowns in it. It would have VA and VB. And then I could do a process of simultaneous equations to combine the equation I've just got, VA plus VB equals 17, and the new equation, and I could solve for my two unknowns. But to simplify things a little bit, I'm going to take moments about point A. That means one of my unknowns, VA, passes through the point about which I'm taking moments, and so will disappear from the moment equation. And so that equation will yield a value for VB. So the sum of the moments about point A must equal 0. I'll assume that clockwise moments are positive. And so what do we have? We have, well, first of all, let's deal with this moment here, 15 kilonewton meters. A moment will appear in a moment equation, obviously without any lever arm. Okay, so we're going to have it acts to produce a counterclockwise rotation of the structure about point A. So that will be a negative 15. So that's from my bending moment externally applied. Now let me see, minus 14.5 meters, that's the length of the structure, times VB. And what else? Plus 14.5 meters times the 7 kilonewtons, that's this guy up here. Plus, let's deal with the resultant, 10 kilonewtons times 10 meters is the lever arm. So 10 by 10. And what do we have? All of that equals 0. So now the only unknown in this equation is VB, and so we can evaluate VB equal to 12.86 kilonewtons. Okay, and again, positive number means that VB is in fact acting in the direction that I assumed when I drew it, acting upwards. Now we can sub back into our previous equation, this guy down here, and we can work out that VA is equal to, it's going to be 17 minus 12.86, which is 4.14 kilonewtons. Okay, job done. So we've confirmed that the horizontal reaction is 0 because there's no externally applied horizontal forces, and our remaining two equilibrium equations have allowed us to work out VA and VB. Okay, so hopefully you were able to work through that yourself.